This is problem number 4 on practice with section 4.6. Okay, so this is from that worksheet. Problem number 4 says a particle moves along a curve y equals the square root of 1 plus x cubed.
What is that little symbol next to 4.6?
Oh, that's section, sorry. That means section. You'll see that when you register for college classes. It says, as it reaches the point 2, 3, the y-coordinate is increasing at a rate of 4 centimeters per second. Someone talk to me about what all that jazz means. Like, what is all that stuff? Tomorrow.
Well, it says that since the y-coordinate is increasing, that means that the y dt is 4
Good.
centimeters per second, and then it also gives you a coordinate point, so you could plug that in for stuff in the equation.
So we're saying when x equals 2 and when y equals 3, we know that the rate of change of y is 4 centimeters per second. Okay? That's what all that stuff means. So my question is, if you've got a particle moving along this curve, is its location for x changing, yes or no?
Yeah.
Yeah.
Is its location of the y value changing if it's moving?
Yeah.
Okay, so I'm not plugging anything into this yet. If you have quantities that change, you have to keep them as variables. I need to take the derivative of this with respect to time. What might I want to do before I do that?
The square roots.
What do you mean?
Make it y equals 1/2 times 1 plus x cubed to the negative 1/2.
No, that would be the derivative.
That would be working on the derivative.
Oh, sorry.
Yeah, no, I know what you mean.
Yeah, she knew what I meant.
Well, don't get cocky about it. So dy dt then. Okay, so now Cameron, go ahead.
So now it's 1/2 times 1 plus x cubed to the negative 1/2 times, do you want to keep going? Times 3x squared.
Good. Okay, there's that chain rule that we have to keep track of.
And then it said dx.
Times.
Oh, times dx.
There you go.
We didn't always do that.
Right, we didn't, right?
Well, we didn't because we weren't talking about things with respect to time. We just said how did x correspond to its change with y.
Okay.
So, or how did y change with respect to
We
x.
did do that when we did implicit
So,
differentiation.
and this is implicit,
Yeah.
exactly. Okay, so the question is, what is dy dt? Got a 4. And then from there, you're just plugging and chugging and simplifying. Are we good with it? Or do I need to keep going?
So you don't plug in
I don't plug in what?
3.
For y? Nope. Sneaky them, they gave us too much information. And then dx dt is the only thing I know, which is what I was looking for. Coolio. Okay. Alright, problem number 5 is saying that we've got this nice little snowball and it's melting so that the surface area decreases at a rate of 1 centimeter squared per second. Find the rate at which the diameter decreases when the diameter is 10 centimeters.
Salud.
First things first, we're talking about surface area. The surface area for a sphere is 4 pi r squared.
And you would get.
I would provide that to you. 4 pi r squared. So if this surface is decreasing at a rate, what does that mean to you? Change it to calculus talk. The surface area decreases at a rate of 1 centimeter squared per minute. Someone who hasn't yet volunteered information today. Sarah, go.
It's a negative velocity. Or rate of change.
It's a negative rate. What is the rate of change? Like, what are we talking about? Are we talking about SA or are we talking about R?
SA.
Yeah. So we would say we know that dSA dt is negative because it's decreasing. Okay. If this snowball is melting, the radius is also changing. The problem is we want information about the diameter. So before I even worry about doing derivatives or anything like that, how can I swap out this variable so that it's in terms of a variable I want information regarding? Tommy?
Regarding d over 2.
Yeah. And I'm just going to write 1/2 d so that we don't think we have to do product rule, or I mean quotient rule. Yep, Sarah.
Could you solve either like solved it for the radius, and then at the end I multiplied by
Totally
2.
fine. You can do that as well.
Answer by doing it, so that is the way. Maybe I just did it wrong. Maybe
You can.
do it like
You can do it like that as well. Yep. Okay. I want you guys to get in the habit of doing the swap before derivative only because there are going to be times where if you don't do the swap before derivative and you do derivative, you're going to have a lot of missing information that you can't just fill in. Like it worked for this problem because radius and diameter, it was an easy swap, but yeah, do the swap beforehand. So the derivative, now we're going to switch to blue. So we'll have dSA dt. Oh, and I suppose I could have cleaned the, this would be 4 pi, and then this is 1/2 d quantity squared. So what does that equal? 1/2 squared? 1/4, and then times 4 pi. It's just pi. So this whole thing becomes pi d squared.
Oh, that would have been way
Wait,
nicer.
how'd you do that?
I plugged in the 1/2 d.
Yeah.
I squared it, so I got 1/4 d squared, and then 1/4 times the 4. So I just simplified it first.
Got it.
So then once you have pi d squared, the derivative is just pi, and then the derivative of d squared,
2D
2d
times
dd
yeah.
dt. Good times. -1 pi times 2. What's our d?
10.
Yay. And now we're golden. Okay? Questions?